An interstellar visitor dubbed 3I/Atlas is hurtling across our solar system at the moment, its luminosity intensifying twofold every couple of weeks, while it forms a verdant haze stretching roughly 500,000 kilometers wide on its path toward Mars. Scientists had anticipated a mere glimmer. Yet, this celestial wanderer is now shining six-fold brighter than forecasted, baffling ground-based scopes and igniting heated discussions about the forces powering such a dramatic flare-up. Could it be an overzealous core, solar rays vaporizing exotic frosts, or an even more bizarre phenomenon? As its nearest pass by Mars looms in mere weeks, and our planet's line of sight gets lost in the sun's overwhelming radiance, experts are scrambling to reveal the underlying cause. Before 3I/Atlas drifts out of grasp, what propels this extraordinary spectacle? And what mysteries hide within that glowing envelope right now? Positioned at about 2 astronomical units from the Sun, 3I/Atlas sits twice as far from our star as Earth does, equating to around 300 million kilometers distant. Its pace is breathtaking. It's currently zipping along at close to 60 kilometers per second and picking up even more momentum. When it reaches its sun-closest point late in October, that velocity will top out near 68 kilometers per second. To put it in perspective, that's over double the swiftest orbital speed of any solar system planet, and fast enough to span the Earth-Moon gap in little more than an hour. On the magnitude chart, 3I/Atlas has hit level 12. That figure may seem abstract initially, but it means the comet remains invisible without aid to the bare eye. Even dedicated hobbyist stargazers require a decently sized telescope under pitch-black conditions to detect it. Indeed, the gap from magnitude 6, the limit for unaided sight, to magnitude 12 equates to roughly 250 times dimmer. Nevertheless, amid these hurdles, its visible glow has surged well beyond what simulations anticipated. The surrounding coma, a nebulous shroud of vapor and particles encasing the core, has ballooned rapidly. Fresh data indicate it now extends across hundreds of thousands of kilometers, comparable in width to Jupiter itself. This swelling isn't merely eye-catching. It's central to why instruments are registering excess illumination from the comet. With the coma's enlargement comes greater reflection and diffusion of solar rays, amplifying the overall detected brilliance, regardless of the icy heart staying concealed. Leading detection programs and facilities worldwide are monitoring these vital stats. The Atlas Group, which first identified the intruder back in early July, documents every fresh location and luminosity shift instantaneously, updating orbital projections and notifying the minor planet center of abrupt shifts. As the Mars encounter and Sun approach draw near, these core figures, separation, velocity, apparent magnitude, establish the foundation for forthcoming analyses. Come September, 3I/Atlas upended projections with a sharp rise in radiance. The light curve, a tool for charting an object's illumination trends over periods, diverged dramatically from expected trends. This wasn't a minor bump. It triggered widespread speculation in both expert and enthusiast astronomy communities. Central to the enigma stands the comet's coma, that immense, broadening veil of gases and debris cloaking its obscured center. Its growth enhances sunlight's bounce and spread, rendering the whole entity more vivid through lenses. By the start of October, opportunities to view 3I/Atlas from our planet are dwindling swiftly. Night after night, it sinks deeper into the evening glow, inching toward the sun's blinding aura. The solar elongation, the angular separation between 3I/Atlas and the sun, narrows under 30 degrees come October 21st. That's the point where even premier Earthbound instruments falter in distinguishing the comet's subtle sheen from the sky's dominant luminosity. For observers globally, the viable observation slot has shrunk to a narrow post-sunset interval. As the comet hugs the skyline before fading into murk, citizen science groups are hustling to snag final viable shots. Digital communities buzz with accounts of botched tries and occasional triumphs, with skywatchers pushing limits against the advancing dusk. Certain crews orchestrate international efforts, passing the observational baton across time zones like a chain, aiming for extra snapshots prior to the alignment eclipse. Institutional facilities, constrained by protocols safeguarding their delicate gear, have begun retreating. The danger of harming instruments by aiming too near the sun looms large, and most opt against the gamble. The pressure extends beyond mere snapshots. After 3I/Atlas slides behind the sun as seen from Earth, a total information void ensues. No fresh readings, no spectral breakdowns, no means to monitor alterations in glow or form. To researchers, this renders each pre-October 21st sighting indispensable. The solar system's layout is slamming the gate shut, leaving the comet inaccessible precisely when it nears its peak drama. During the active period, the sole opportunity for ongoing surveillance relies on observatories positioned away from Earth's direct view of the sun. This responsibility now falls heavily on probes encircling Mars. For a short interval, the red planet serves as the sole vantage point, offering a prime view of 2I/Atlas. As ground-based observatories on Earth lose visibility amid solar interference, attention turns to a group of satellites orbiting Mars. Various probes contribute unique observational capabilities. The European Space Agency's Mars Express, featuring its high-definition stereo camera and Omega spectrometer, can record visual details and molecular signatures from distances spanning millions of kilometers. The ExoMars Trace Gas Orbiter, outfitted with NOMAD and ACS spectrometers, is tailored to detect subtle traces of gases like water vapor, carbon dioxide, and unusual compounds within the comet's surrounding envelope. NASA's MAVEN, engineered to examine Mars's upper layers, can adjust its ultraviolet spectrograph to detect outflows from the comet's gases and particles, while its plasma sensors track interactions between the solar wind and this extraterrestrial wanderer. The Mars Reconnaissance Orbiter, renowned for its precise, high-resolution imaging system, might discern the comet's core under favorable circumstances. Although following a swiftly moving comet poses difficulties for any probe, the orbital alignment benefits Mars. On October 3rd, 2I/Atlas passes roughly 28 million kilometers from the planet, near enough for these satellites to conduct targeted scans, yet distant enough to sidestep dust avoidance measures that previously complicated comet encounters. Scientists operating the instruments have devoted weeks to modeling scenarios, refining orbital data, and securing limited viewing times. Each group seeks its share of the event. Efforts include capturing visible and infrared visuals to outline the envelope, ultraviolet readings to assess gas output, and plasma records to explore the comet's exchanges with solar particles. Researchers aim to isolate the core as a clear spot distinct from the expansive envelope, and to analyze the composition of substances liberated as the comet warms. No probe guarantees constant monitoring. Schedules hinge on orientation limits, transmission capacity, and the erratic timing of the comet's nearest pass. Yet, just a few effective observations could yield revelations unattainable from Earth-based setups. Precise readings of particles, gases, and charged particles at unprecedented scales for such a cosmic interloper. Currently, Mars holds center stage, with research crews poised to capitalize on this uncommon chance before 2I/Atlas hurtles onward to its solar rendezvous. The initial standout trait of 2I/Atlas is its vivid emerald radiance. Experts in spectroscopy promptly focused on this hue, examining the comet's emissions for molecular clues. Agreement, supported by ultraviolet-stimulated data from both expert and hobbyist observers, identifies diatomic carbon, C2, as the primary source. Solar rays energizing carbon-laden compounds in the envelope propel them to heightened states. Upon settling, these emit a bright green glow, particularly in the Swan bands near 510 nanometers. This hallmark appears in vigorous comets, but 2I/Atlas distinguishes itself with the profound depth of its emerald tone, observable even at 2 astronomical units away. Not all views align on the specifics. Certain groups suggest inputs from ionized carbon monoxide, CO+, or the cyanogen radical, CN, particularly in initial September readings. These too can produce green or blue luminescence under solar ultraviolet, sparking discussions in review forums about calibration methods and noise removal techniques. Nevertheless, the strongest datasets, those with pristine, broad spectral ranges, uniformly indicate C2 as the leading force in the visible envelope. This composition extends beyond aesthetics. The comet's high velocity accelerates the impact of solar energy on pristine ices and grains, stripping volatile elements and blending them into the envelope. Consequently, the emerald shade signals more than carbon presence. It reflects the pace at which the surface evolves during its solar approach. An increasing array of watchers has detected an unusual aspect in 2I/Atlas's form, a subtle extension directed toward the Sun. This unusual anti-tail defies typical comet behavior, where particles are generally pushed sunward by radiative forces, creating a standard tail that trails behind. For 2I/Atlas, the configuration and dynamics align to reverse expectations. As the comet dashes through the inner solar realms at remarkable paces, released dust particles may outpace the core, particularly larger or charged ones. From our earthly viewpoint, this creates a narrow projection toward the Sun, an anti-tail apparent only from precise angles. Plasma specialists note that the swift broadening of the interplay between a comet's coma and its rapid speed generates a tricky setting where magnetic influences compete with gravitational pull. Electrically charged particles trapped amid the solar wind and the comet's personal emissions can channel into tight beams. These features pointing toward the Sun aren't fixed. They hinge on factors like particle dimensions, electrical charge, and shifting solar illumination. The display gets boosted by the distinctive observation angle in late September, as 3I/Atlas's path aligns Earth nearly flat with its debris layer. At this point, sightings of a sunward anti-tail on 3I/Atlas are still unconfirmed. Hobbyists and certain expert groups have noted potential signs, yet no verified photos or exact data have appeared in scientific journals. This occurrence isn't unfamiliar in comet studies, though seeing it on an interstellar body moving at such paces is exceptional. Currently, the anti-tail contributes extra mystery to this erratic guest, underscoring the intricate dust-plasma interactions as 3I/Atlas races sunward. Each comet entering our solar system carries its distinct traits. Yet 3I/Atlas distinguishes itself even in elite interstellar ranks. The initial pair of such visitors, Oumuamua and 2I/Borisov, define the anticipated range for stargazers. Oumuamua, spotted in 2017, resembled a barren, elongated cigar with no evident coma or tail, just a rotating fragment that glided quietly through the inner system. 2 years on, 2I/Borisov showed up bearing standard comet signs, a vivid azure coma, a conventional dust trail, and a makeup heavy on water and cyanide. Similar to the periodic icy drifters circling the Sun, 3I/Atlas defies easy placement in those molds. Its coma isn't merely expansive but strikingly verdant, owing to intense diatomic carbon glow rare in typical local comets. The sudden six-fold brightness leap beyond forecasts lacks matches in Oumuamua's subdued trip or Borisov's gradual buildup. And whereas Borisov's tail flowed anti-sunward predictably, 3I/Atlas suggests a sun-facing anti-tail, a trait common in the scarcest homegrown comets but virtually absent from extrasolar ones. Compared to fresh arrivals like C/2023 R2, Swan, and Assassin 1, which revealed their activity flares, 3I/Atlas occupies its own tier. Its velocity, composition, and erratic patterns compel scientists to reassess the divide between native comets and those born in far-off stellar realms. For cataloging experts, the issue goes beyond mere tagging. Every oddity in 3I/Atlas's repertoire offers insight into dynamics that could have molded minor celestial objects galaxy-wide. The implications loom large. Each fresh observation risks overturning long-held theories on comet nature and the tales these travelers share of their origins. Post-perihelion, 3I/Atlas will dim quickly, probably swifter than its earlier flare-up. Projections indicate a steep decline in visibility as it hurtles outward, with the coma contracting and scattering into obscurity. Spotters will need bigger gear. A 20 cm aperture scope sets the baseline, though only top-tier sensors might reveal beyond a hazy blot. Naked eye or basic visual chasers will lag behind its swift exit, demanding stacked exposures and meticulous noise removal to monitor residual glow. Comet tracking now leans on digital tools and group efforts, online hubs, and volunteer projects, ranging from chat-based communities to formal outfits, deliver instant intel on location, luminosity, and shape. They aggregate amateur telescope feeds worldwide, run them via communal software, and share brightness graphs for all to track. For enthusiasts, this marks a milestone, a genuine interstellar body's decline documented live by non-pros. Science's quest persists through the dimming. Every brightness plot, spectral reading, or contested sighting builds the broader enigma. How do extrasolar comets act amid an alien star system's pull? What lessons from their makeup, particles, and waning shine reveal about galaxy-spanning planet formers? These inquiries extend past pros, welcoming telescope owners, computer users, or mere wanderers to contribute as 3I/Atlas recedes into shadow. Ground views end after October 21st from Upper Conjunction, making the October 3rd Mars encounter the final chance for detailed, close-up scans with multiple tools. No full timetables for Mars satellites have surfaced yet. Details on its trajectory have been withheld, creating uncertainties regarding future observations. Unlike Oumuamua and 2I/Borisov, 3I/Atlas exhibits a blend of traditional cometary traits alongside unusual characteristics. Insights into its solar passage, makeup, dimming pattern, and physical dynamics will shape subsequent research on extraterrestrial objects. At present, the essence of 3I/Atlas stays an unresolved puzzle in science, backed by solid observational data and pending its subsequent perihelion approach.